title of our project is Line Integral of Vector Field.
What is a line integral? A line integral is a method to calculate the total value of something along a path or curve. Unlike normal integration on straight lines, line integral are used to calculate a long curved path in 2D or 3D. There are two types of line integral. The first one is scalar line integral. It is for quantities like temperature, density, or energy. For the second type of line integral is vector line integral. It is for quantities like force, velocity, or electric fields. A simple example is if we have a wire that bends in space with different densities at each point, we use a line integral to find the total mass of the wire by following exact shape. There are three theorems in this line integral. The first theorem is the arc length theorem. It is to calculate the length of a curve using this equation. In 2D, the formula is square root dx dt square plus dy dt square, while in 3D, the formula is square root dx dt square plus dy dt square plus dz dt square. For the second theorem, the formula can be written as this. For the third theorem, it is for work done by a vector field. For the work done by a vector field F along a curve can be written as this. Scalar line integrals are used to calculate quantities like mass, energy, or density along a curve. Vector line integrals are used to calculate the work done by a force on a particle along a certain path.
Case study 1. The case study is about a worker is pulling a heavy load using a cable that spirals upward. The particle moves through a 3D space under a swirling wind force field. Find the work done by the force field, where Fxyz equal to yi plus zj plus xk. On a particle moving along the spiral path, Rt equal to cos ti plus sin tj plus tk with t from 0 to 2 pi. Now moving to the manual calculation. Step 1. Identify the force field, where the Fxyz equal to yi plus zj plus xk. Step 2. Define the parametric spiral path. Rt equal to cos ti plus sin t plus tk. Step 3. Find the derivative of the path, where r prime t equal to negative sin ti plus cos tj plus 1. Step 4. Substitute rt into the force field, where frt equal to sin ti plus tj plus cos q. Step 5. Compute the dot product for frt and rt. Then it will be equal negative sin square ti plus t cos tj plus cos. Set up the line integral to find the work done. Integrate negative sin square ti plus t cos tj plus cos tk from 0 to 2 pi. To solve this integral, use the identity for sin square t and integration by part for t cos t. Next, we will evaluate each term of integration, so the final result is w equal to negative pi. Therefore, the work done by the swirling wind force field on the particle moving along the spiral cable is negative pi.
So moving forward with the maple comment for case study 1. Firstly, we loaded vector calculus and plots in order to access the functions needed in order to visualize our problem solving. And then we establish F and R, which is the parametric equation. And then we differentiate the R using the function diff. And then we substitute the value of xyz with R. Then we apply a dot product and we calculate the work done using the integral of f dot dr dt. Then using the space curve function, we display a graph of a particle that moves under a swirling wind force field.
For case study 2 is about a metal ring is lying flat on the table. The temperature varies along the ring, so to calculate the total heat distributed along the ring, we need to evaluate the line integral, where integration of x squared plus y squared ds, where the curve C is a circle of radius 3 in the xy plane given by the parametric equation xt equals to 3 cos t, yt is equal to 3 sin t, zt is equal to 0, where t is between 0 until 2 pi. The solution for case study 2 is by following the formula above. So for step 1, we find the fxy, which is equals to x squared plus y squared. Step 2, we rewrite the parametric equation where xt equals to 3 cos t, yt equals to 3 sin t, and zt is equal to 0. Then we differentiate the parametric equation, we will get x prime t equals to negative 3 sin t, y prime t is equal to 3 cos t, and z prime t is equal to 0. For step 4, we'll find fxt, yt, zt, where we substitute the parametric equation into the function x squared plus y squared. So when we calculate it, we will get 9 as the answer. Step 5, we find ds, where ds equals to norm r prime t dt. To find norm r prime t, we need to square root the dx over dt squared plus dy over dt squared plus dz over dt squared. So when we calculate it, we will get the answer is 3. Step 6, we find the integral fxy ds, where we follow the formula integral fx dy dzt multiply with norm r prime t dt. So we know the value fx dy dzt is 9 and the value of norm r prime t is equal to 3. We substitute the value into the formula and then we will get 54 pi as the answer.
So for the mapper command for case study 2, as usual, firstly we loaded vector calculus and plots. Then we establish f and also r as the parameter equation. We find the r by differentiate it, and then we also calculate the magnitude of the differentiated dr, which we will get 3. Then we substitute the value of r into f, which makes it the f capital, and then we calculate the integral of w, which is the heat distribution. Using the space curve function, we display the heat distribution throughout the ring. So for conclusion, this project has explored concept and application of line integral, both scalar and vector field, through a detailed manual calculation and mapper software verification. We have demonstrated how line integral can be used to evaluate physical quantities such as work done and heat distribution along a curve. These real-world examples highlight the practical significance of line integral in fields like physics and engineering, reinforcing their value in solving complex vector calculus problems. Thank you very much for watching the video. Like and subscribe if you like.